I'm now going to talk about vitamins B2 and B3. Both are oxidation reduction cofactors with different functions. We've seen a riboflavin derivative already, FAD or flavin adenine dinucleotide, which is the oxidized form. It's a molecule that can be reversibly oxidized and reduced with the addition of 2 protons and 2 electrons. Unlike the B3 derivatives, there's also a single electron intermediate which is radical and we'll discuss later. The addition of the equivalent of a whole hydrogen atom is a redox reaction, unlike the addition or removal of a proton, which is an acid-base reaction. Niacin is metabolized to NAD+ or nicotinamide adenine dinucleotide, which is reversibly reduced to NADH, this time with 2 electrons and 1 proton, or the equivalent of a hydride ion. The phosphorylated form NADPH undergoes the same reactions but has different uses that I'll discuss later. There's also another form of riboflavin derivative, which is flavin mononucleotide, FMN, which undergoes the same reactions as FAD. Nicotinamide can serve as a prodrug for niacin or be metabolized to NAD via a different pathway. Tryptophan, the essential amino acid, can also be metabolized to NAD. The clearest distinction between B3 cofactors and B2 cofactors is that B3 factors are soluble and diffuse between different sites, acting as shuttles for electrons between different redox reactions. FAD and FMN function as part of protein complexes, typically for one reaction or a coupled reaction. B2 deficiency is rare and causes a syndrome called ariboflavinosis, while B3 deficiency causes pellagra. In these factors used in metabolism, NADH is used to shuttle electrons between various catabolic pathways and the electron transport chain. FAD is most prominently featured in the succinate dehydrogenase reaction in the citric acid cycle. It's not just a cofactor, it's part of the protein complex, which also makes up complex 2 of the electron transport chain. It's also featured in the first step of beta oxidation as part of acyl-CoA dehydrogenase, which are a family of enzymes for different fatty acid substrates. FAD is much more widespread than you might think. The 3 thiamine-dependent mitochondrial dehydrogenase complexes are all flavoproteins. They also require lipoic acid and magnesium. Electron transport chain complex 1 features a flavin group, this time FMN, which accepts electrons from soluble NADH. When we talk about a chain, we're literally talking about a series of coupled redox reactions ultimately driven by molecular oxygen. It does get a lot more complicated than just B2 and B3. There are numerous redox cofactors that the body synthesizes for different applications. For example, the next step in the chain features an iron-sulfur cluster. This is a family of intermediate chemical structures that can participate in redox reactions. They are made up of cysteine residues converging to create a lattice of different numbers of iron and sulfur atoms, as you can see by the structures in the corner. Next, we have an entirely different redox carrier, coenzyme Q. This would be a vitamin akin to riboflavin if we weren't able to synthesize it. Ubiquinone is its oxidized form. If you add 1 electron and a hydrogen ion, you have a radical intermediate called ub-semiquinone. Finally, if you add another electron and another proton, you have ubiquinol, the reduced form. Apart from the aromatic structure, it has a long polyunsaturated carbon tail, making it partly lipid soluble. This allows it to diffuse between complexes in the inner mitochondrial membrane. Complex 2 also has an iron-sulfur cluster, followed by a Haem structure, which is an iron-iron suspended in a porphyrin ring, another common redox cofactor. Ultimately, it passes its electrons to coenzyme Q to diffuse to the next complex. You might wonder, based on some misleading textbook illustrations, how FAD2 from beta oxidation makes it to complex 2 if complex 2 is part of succinate dehydrogenase. The answer is that it doesn't. It has its own chain of flavoproteins and its own equivalent of complex 2. First, it reduces the FAD in a matrix protein descriptively called electron transfer flavoprotein. ETF is then oxidized by ETF dehydrogenase, a membrane-bound protein that functions as the beta-oxidation version of complex 2. Then it passes its electrons to complex Q via another iron-sulfur cluster. All the reduced Q cofactors go to complex 3. The job of the electron transport chain is to shift protons from the mitochondrial membrane to the intermembrane space, which is driven by the energy of this redox chain. In complex 1, while tempting to picture it as the addition and removal of protons to the flavin groups, the mechanism is likely indirect, with 4 hydrogens shuffled by a conformational change in the complex, while the reduction of coenzyme Q is taking place. The mechanism of complex 3 is tricky because a few things happen simultaneously. Essentially, it oxidizes 2 QH2 molecules back to the reduced Q form, liberating 4 electrons. 2 electrons are shuttled through 2 heme groups to the matrix side, where they reduce a third Q complex to QH2. This gives a net reaction of oxidizing 1 QH2 molecule. The 2 oxidized QH2 molecules release their hydrogen ions into the intermembrane space, providing complex 3's contribution to the proton gradient. The 2 remaining electrons are shuttled through an iron-sulfur cluster and each reduce a cytochrome C molecule. Cytochrome is a protein with a heme in it that takes place in redox reactions. Unlike Q and NAD, each cytochrome molecule only carries 1 electron, and it does this by changing the oxidation state of its ion from 3+ to 2+. Unlike coenzyme Q, cytochrome is water-soluble and diffuses freely in the intermembrane space, where it reaches complex 4. Complex 4 is also known as cytochrome oxidase because it oxidizes cytochrome C back to +3 with the aid of molecular oxygen. The first step uses copper ion as a cofactor. The complex 4 reaction is also tough to follow because it involves multiple state changes at the active site, as well as different currents of electron and proton flow. I've included the diagram from the reference I used on the right, although I did simplify it in the main diagram. Essentially, it involves an active site with 3 components, one of them being a heme group, which I've depicted in the center. You can see that in the current state, it has an ion 3+ with a hydroxyl group attached to it. The active site also features a second copper ion, currently 2+ with a hydroxyl attached. And finally, it features a tyrosine with its alcohol group. In the next step, half of the electrons pass from the cytochrome C, reducing both the iron and the copper. Protons from the matrix side combine with the hydroxyl groups, making water. Then the molecular oxygen reaches the active site, reoxidizing the iron and copper and producing a tyrosine radical. Finally, other electrons reduce the iron and tyrosine radicals, and some additional protons return the active site to its original state. In the process, it shuttles further protons from the matrix to the intermembrane space, half as many as complexes 1 and 3. The mechanism of this proton shuttling is apparently controversial, but likely involves conformational change similar to complex 1. Now, if you are following this extremely closely, you might have noticed some of my coefficients don't match like in the diagram on the right. Essentially, I've halved the number of protons, electrons, oxygen, and water to match the flow of electrons to the rest of the chain. I couldn't do this for the active site because you'd have half a tyrosine, etc. So if that bothers you, here in purple are the corrected coefficients to match the active site. Okay, those are gone again. If you ignore the active site in the middle, all the quantities in and out should match. For one FADH2 or NAD+, NAD2H, 2 electrons flow, which equates to 1 reduced coenzyme Q, 4 protons through complex 3, 2 cytochrome C, 2 protons through complex 4, and half a mole of oxygen converted to 1 water. Energy catabolism is not the only thing that uses redox cofactors. Let's look at another cellular process, which is the synthesis of heme. As we've seen, heme in itself can be a redox cofactor in the form of cytochromes. Its synthesis is pretty cool because it takes some very basic organic molecules and creates a complex ring structure with a ferrous ion suspended in it. Over 80% takes place in the bone marrow to make hemoglobin, and most of the rest takes place in the liver. In both tissues, the process starts in the mitochondrial matrix. Our first precursor is succinyl-CoA, which we know from the citric acid cycle. The next step attaches a glycine molecule and requires vitamin B6, producing delta aminolevinulate, which moves to the cytosol. Two of these are then fused together to create porphyrobilinogen. Then 4 of these are deaminated, forming an open ring structure. Next, the ring is closed. Some carboxyl groups are trimmed off, and the resulting corpoporphyrinogen enters the intermembrane space. It's then transformed into protoporphyrinogen using another iron-sulfur cluster and S-adenosyl methionine, which is discussed in the B12 folate section. Next, some of the bonds are further oxidized with the aid of FAD, and the resulting protoporphyrin returns to the matrix. Finally, iron is added to the center with the aid of another iron-sulfur cluster forming heme. The cell needs to be very cautious about how it handles iron for reasons I'll discuss shortly. Heme is used in multiple products including hemoglobin, myoglobin, various redox enzymes, some of which we're about to discuss. The clinical relevance of this pathway is a group of rare disease known as porphyrias. There's at least one type of porphyria for each enzyme in this process. Riboflavin deficiency can also inhibit heme synthesis, and then lead poisoning inhibits 2 enzymes in this process, causing symptoms similar to porphyria. The key rate-controlling enzyme in heme synthesis is delta aminolevulinate synthase. It is inhibited by heme in a negative feedback mechanism and incidentally by glucose. An interesting thing about porphyria is that there are 2 very different pathological processes happening. Acute porphyrias are not strictly diseases of heme synthesis. They are diseases of the regulation of heme synthesis, particularly in the liver. This is because there are 2 subtypes of ALA synthase 1 and 2. 2 is present in the bone marrow, while 1 is present in most tissues, especially in the liver, and it's inducible. The first 2 steps in the heme synthesis process are relatively small molecules, but they are neurotoxic. This doesn't cause a problem unless there's a bottleneck somewhere proximally, and if heme synthesis is upregulated. Specifically, it needs to be restricted at ALA dehydratase or PGB deaminase, the first 2 cytosolic enzymes. This means that the extremely rare ALA dehydratase deficiency and the much more common acute intermittent porphyria present purely with acute neurovisceral attacks. These only happen when heme synthesis is upregulated, particularly in response to drugs, steroid hormones, or a fasting state. This causes a temporary spike in these neurotoxic intermediates that subside when the trigger ends. There's 2 other porphyrias, which are actually mixed porphyrias because they can cause chronic cutaneous symptoms and acute attacks. The reason they have acute attacks is the accumulating porphyrins protoporphyrinogen 9 and coproporphyrinogen 3 inhibit PGB deaminase, the same enzyme that's deficient in acute intermittent porphyria. As a result, all 4 of these porphyrias can cause acute attacks, though variegate porphyria to a lesser extent. How do they present? Most commonly, there is severe neuropathic abdominal pain without localizing features. They can also have significant autonomic dysfunction. Peripheral and autonomic nerves are most severely affected due to the lack of a blood-brain barrier, but in severe cases they can also develop neuropsychiatric features such as psychosis. After multiple attacks, you may also see peripheral neuropathy. So what sets them off? Like I said, fasting, hormones such as progesterone, and certain enzyme-inducing drugs. Major culprits include alcohol, barbiturates, and phenytoin, but a handy rule is that any strong inducer of cytochrome P450 is a possible trigger, as heme is needed to produce more cytochrome. AIP is more common in women, and attacks may coincide with the luteal phase of the ovarian cycle. The main treatment is intravenous heme or hemin, which inhibit ALA synthase, though glucose can have some benefit. The other syndromes seen in porphyria are due to accumulation of the larger ring structures further down the pathway. In UPG synthase deficiency seen in congenital erythropoietic porphyria or Gunther disease, the accumulating hydroxymethylbilane circularizes into a non-physiological compound UPG1, which is then formed into CPG1, which is a metabolic dead end and also toxic. In the cutaneous porphyrias, these porphyrin structures accumulate through the body and can be oxidized by sunlight, causing type 4 hypersensitivity reactions. These manifest as blistering skin lesions days after exposure to sunlight. CEP is the most severe form and also causes hemolytic anemia. In some cases, it necessitates a bone marrow transplant. Porphyria cutaneatata is the most common porphyria in most populations and often has an acquired component due to the presence of inhibitors of the enzyme. HEP is the severe congenital mutation of the same enzyme. The next two are the combined or neurocutaneous porphyrias that cause blistering photosensitivity as well as the acute neurological attacks for reasons that we discussed before. The main treatment of all of the cutaneous porphyrias is the avoidance of sunlight. Finally, you have two remaining cutaneous porphyrias at either end of the pathway. Both are actually relative deficits of the final enzyme ferroketolase. Obviously, in erythropoietic protoporphyria, you have a buildup of the final intermediate, which is protoporphyrin 9. This actually causes an acute, painful photosensitivity immediately after sun exposure, like a bad sunburn, and bullae are less common. It can also cause cholestatic liver disease in a minority of patients. All porphyrias are due to a buildup of heme precursors, but the pathway is essential for life, so most porphyrias are autosomal dominant loss of function mutations, or in the case of CEP, HEP, and ALA dehydratase deficiency, they are autosomal recessive but with approximately 5% preserved function. The big exception comes to ALA synthase, because succinyl-CoA and glycine aren't particularly toxic and the deficiency doesn't cause porphyria. It actually causes an X-linked recessive sideroblastic anemia from lack of heme. The gene can cause porphyria though, in rare cases, with an X-linked dominant gain-of-function mutation, which accelerates the whole pathway. Unlike the acute porphyrias, there's no early bottleneck around PGP deaminase, so the natural limitation is actually at the final step, and as a result, the symptoms are identical to erythropoietic protoporphyria. But how does sunlight oxidize something? We need to talk about reactive oxygen species. To start, I'm going to skim over some basic chemistry as it will be important. Let's look back at the periodic table. It's divided into 4 blocks based on which atomic orbital is filling up at the time: S, P, D, and F. We're going to focus on S block and P block to keep things simple. S block has one orbital and holds a maximum of 2 electrons of opposite spin. P block has 3 orbitals, so it holds a maximum of 6. They start with 1 electron in each orbital and then fill up the remaining ones to give a full shell of S2p6, which gives us the octet rule. The octet rule simply states that one of these relatively simple elements can have a maximum of 8 electrons in its outer shell, and that the element will try to achieve this full shell configuration through chemical bonds. This is a chlorine atom. It has 7 electrons in its outer shell. In practice, that makes it a highly unstable chlorine radical, as it doesn't want to have this unpaired electron, and it makes it violently reactive. This is why, in practice, we see chlorine as diatomic molecules covalently bonded together. Elemental sodium has 1 electron in its outer shell, but it's not a radical because it has low electronegativity and the electrons exist in diffuse metallic bonds. These react together to form sodium chloride, where sodium loses its electron completely, gives it to chlorine, forming a positive and negative ion respectively. This is a redox reaction, as it involves a single electron transfer. Sodium is oxidized because it lost an electron, while chlorine is reduced because it gained one, and you can confirm this with a change in oxidation numbers. Next, we'll look at a Bronsted-Lowry acid-base reaction. Hydrogen chloride, unlike sodium chloride, is covalently bonded, although in a polar fashion. The acid is a proton donor, and the oxygen in the water accepts the proton on its unbonded electron pair, sharing its electrons in a coordinate covalent bond. This is not a redox reaction, as in either molecule the proton has an oxidation number of +1 and no electrons are transferred. Next, we have a Lewis acid-base reaction, which are extremely common as substitution reactions in organic chemistry. A Lewis acid that lacks an electron pair or an electrophile gains one from the Lewis base or nucleophile, forming a coordinate covalent bond. This is also not a redox reaction. Now this is a redox reaction, the oxidation of ethane to ethene. Using the rule of -1 for each hydrogen, the carbons have an oxidation state of -3. They are oxidized to -2 with the formation of a double bond and the loss of both 2 electrons and 2 protons. Take note of this, because the bonds contain at least 2 electrons, it's very uncommon for a single electron redox reaction without forming a radical. So how do radicals work then? In a usual reaction, such as the ionization of hydrochloric acid before, the bond is broken asymmetrically, with both electrons going to the more electronegative atom, forming a positive and negative ion. This is known as heterolysis. Radicals can be formed through homolysis, when the atoms split symmetrically, each taking their own electron. An example would be a diatomic halogen molecule like chlorine splitting to make 2 chlorine radicals. This process always takes energy, which could be provided in the form of a high-energy photon, for example. Radicals are interesting and dangerous because they are so unstable that they naturally cause chain reactions. This would be considered the initiation step. Next is propagation. One of the radicals meets another molecule and induces another homolytic split, forming a new covalent compound and a new different radical. For example, a chlorine radical might encounter a hydrogen attached to an organic molecule, but instead of removing a proton, it needs that electron, so it removes the neutral hydrogen atom. This process is called abstraction and would form hydrogen chloride and an organic radical. The organic radical could react with a chlorine molecule, replacing its lost hydrogen with an abstracted chlorine and leaving a new chlorine radical to continue the chain reaction. Abstraction is a redox reaction because you are taking an electron with it. Loss of an electron is oxidation, and radicals are typically powerful oxidizing agents. Propagation reactions can use or release heat, making them enthalpically favorable or unfavorable depending on the molecules involved. The final stage is termination. The chain reaction continues until two radicals find each other and bind together. This is always enthalpically favorable, but could be relatively unlikely in the biological setting because hopefully you have a low concentration of free radicals at any given time. The alternative is that a radical species forms which is more inherently stable, typically because it has double or aromatic bonds and can diffuse the radical into a resonant structure. This remains a radical, but it's less likely to react and cause damage. There'll be several examples that come up soon. We're now going to look at some examples, including the most important radicals in the biological setting. This is a diatomic oxygen molecule. The reason I haven't used it as an example so far is that oxygen's a bit complicated. The usual oxygen we breathe is actually a diradical because it has an unpaired electron on either side. You might have been taught that it simply has a double bond, but that was a lie to avoid confusing us. Instead, it contains a single sigma bond and two half pi bonds. This form is known as triplet oxygen, and it's has relatively low reactivity as reactive oxygen species go. As far as I understand, the reason for this, and the reason that we don't all burst into flames right now, is that the lone electrons on either side have the same spin, and to react, it would have to find a molecule with two opposite spin electrons to match. There is a form of oxygen with a double bond called singlet oxygen, which is considered a reactive oxygen species. This quickly devolves into quantum physics, which is inherently confusing, and I won't dwell on it too much. As a neutral molecule, oxygen has an average oxidation state of 0. I'm now going to sequentially add one electron, reducing the average oxidation state by half, because it's -1 divided by 2. First we have the superoxide radical. This is a very important reactive oxygen species in the biological setting, although it's not the most unstable one we'll come across. It has an average oxidation state of -1/2 because has a formal charge of -1 divided by 2. Next we have peroxide, which is not a radical, but it is more unstable than oxygen. The oxygen has now been reduced to an oxidation state of -1, which is halfway to its usual -2 configuration. Notice how adding one electron formed a radical, but adding two electrons did not. We're more familiar with hydrogen peroxide, which is the aqueous protonated form. This is the same oxidation state because acid-base reactions are not redox. Let's add an electron. Now the molecule has split into a water and hydroxyl radical. Not to be confused with hydroxide ions, this is a neutral radical molecule which is the most reactive oxygen species we'll see. The oxygen in hydroxyl radicals have the same oxidation state as in peroxide, but the average has dropped again to -1.5 because of the more reduced water. Let's add one more hydrogen. Finally, we have the most stable form, oxide, in this case hydrogen oxide or water. This has the -2 oxidation number that we usually see for oxygen in organic compounds. In the biological setting, the middle three of these are considered reactive oxygen species, even though peroxide is not technically a radical and oxygen technically is. They can be compared to each other in terms of reactivity or instability. The most reactive by far is the hydroxyl radical, with a half-life of about a nanosecond before it reacts with a nearby molecule. This is too fast for an enzyme to be able to detoxify it. Next is superoxide, which has a variable stability between microseconds and seconds based on the environment. Remember that a millisecond is 1,000,000 times longer than a nanosecond if you want to compare the two. In the body, the half-life of superoxide is determined by antioxidant enzymes that we'll discuss shortly. Hydrogen peroxide is pretty stable. For example, it can stay in a bottle long term as long as there's nothing to catalyze its decomposition. Molecular oxygen, as discussed, is also pretty stable, and then water is the most stable. So where do radicals come from? The main source is oxygen. I'm going to talk about some reactions that generate and remove reactive oxygen species in the body. For a start, oxygen can turn into superoxide in the presence of certain transition metal ions. Remember, transition metals have a d orbital to work with, so there's a lot more potential chemistry that can happen. This is also why the presence of metal ions such as iron or copper is tightly controlled within the body, and they're usually bound to proteins such as ferritin. Iron 2+ or ferrous iron can also react with hydrogen peroxide, turning it into a hydroxyl radical and hydroxide ion. This is known as the Fenton reaction. For something to work as a catalyst, it needs to be unchanged when the reaction finishes, otherwise it's just another reactant or product. And when I say unchanged, that includes the oxidation state. This means that in either of those reactions would be limited by the remaining concentration of iron or copper. But if one of them was to run in reverse, that ion would be recycled and you essentially have a non-consumed catalyst. This is known as the Haber-Weiss reaction, and it's the other major chemical reaction you'd come across. It's just the Fenton reaction combined with the reverse of the superoxide formation from oxygen and then added together. It does mean that superoxide can form hydroxyl radicals in the presence of hydrogen peroxide, which is not ideal. How does the body get rid of these molecules? The first enzyme we'll look at is superoxide dismutase. Dismutase means it's taking two radicals and terminating the reaction, turning one into dioxygen and the other into peroxide, which are both much less reactive than superoxide. There are three subtypes of superoxide dismutase which use different trace minerals as cofactors. Superoxide dismutase 1 is present in the cytosol, SOD2 in the mitochondria, and 3 extracellularly. 1 and 3 require copper and zinc, and then 2 requires manganese. As with the Haber-Weiss reaction, the metal catalysts do change their oxidation states, but they're recycled back in the same reaction. This is a recurring theme with antioxidant and other redox enzymes. What do we do with the peroxide once it's been made? There's two major pathways for this. One is another enzyme called catalase. Just like superoxide dismutase, it requires 2 hydrogen peroxide as it's a two-step reaction that recycles the metal catalyst, in this case iron. The first step reduces a peroxide to water, while the second arm recycles the catalyst and produces a water and oxygen molecule. Those are two simple mechanisms for detoxification of ROS, but there are many others. And specifically, there is a more efficient method of removing peroxide, which is the use of glutathione. Glutathione is a tripeptide molecule that's widely used in biology as an antioxidant. The body makes it from 3 amino acids, glutamate, cysteine, and glycine. The cysteine is the rate-limiting reactant and the central component of a glutathione. When we give N-acetylcysteine in medicine, it is as a pro-nutrient to make cysteine to make glutathione. The first step combines glutamate and cysteine, though not in a traditional peptide bond. The side chain carboxyl group of the glutamate is bound to the cysteine, hence the gamma in the name of glutamylcysteine. Then a glycine is added on the other side in a peptide bond by glutathione synthetase. The really useful thing about glutathione is that 2 of them can be reversibly oxidized to make a disulfide bridge. In this case, the oxidizing agent is hydrogen peroxide and the catalyst is glutathione peroxidase enzyme, which uses selenium as a cofactor. This reduces 1 hydrogen peroxide molecule to 2 benign water molecules. For this to be an effective antioxidant, glutathione disulfide needs to be recycled back to glutathione. This is done by glutathione reductase, which uses FAD as a cofactor and NADPH as a reducing agent. Based on equilibria, you could predict that for this to work most efficiently, the body should have a high concentration of NADPH relative to oxidized NADP+. Now, occasionally, the cell actually wants to make free radicals, particularly in the immune system. NADPH can also be used to produce superoxide with the flavoprotein enzyme NADPH oxidase. Superoxide is turned into then turned into peroxide via superoxide dismutase. Another enzyme, myeloperoxidase, uses an iron cofactor and a radical intermediate to produce hypochlorous acid. Hypochlorous acid is a reactive chlorine species that cells like neutrophils and macrophages use to damage pathogens. You're probably most familiar with its salt sodium hypochlorite, which is the most common ingredient in bleach. Nitric oxide is another radical used by the body, but a relatively stable one. In aqueous solutions, it has a half-life of minutes, although seconds in biological settings. Nitric oxide synthase is a complex enzyme with 3 isoforms: neuronal, inducible, and endothelial. It requires numerous cofactors and multiple redox cofactors, including FAD, FMN, a heme group, as well as NADPH and molecular oxygen as co-reactants. The reason it's so complicated is that the oxidation reaction involves the transfer of 5 electrons to the nitrogen on the arginine side chain. As we saw previously, the reduction of oxygen to oxide takes 4 electrons, and 8 in this case because there's 2 of them. 5 electrons are provided by the arginine, and the remaining 3 by 1.5 NADPH. Nitric oxide is an important gaseous signaling molecule used, for example, to stimulate smooth muscle relaxation by the GMP pathway. As a radical, nitric oxide can react with other radicals such as superoxide to produce peroxynitride. This is a non-radical reactive nitrogen species analogous to peroxide. Now there's other sources of superoxide besides metal ions, and we'll look at some of the major ones in practice on the next slide. Most reactive oxygen species are generated from oxygen, and we'll use superoxide as a stand-in here. We've already looked at some of the simplest non-enzymatic reactions, such as with ferrous iron. The primary source of reactive oxygen species in our bodies is mitochondria. They generate 90% of reactive oxygen species, with between 0.2 and 2% of molecular oxygen that's consumed in respiration, forming reactive oxygen species like superoxide. The main sources are electron leakage from complex 1 and complex 3, and a smaller amount from complex 2, though minimal from complex 4, which apparently handles oxygen very efficiently. Flavoprotein enzymes such as alpha-ketoglutarate and pyruvate dehydrogenase complexes can also generate some reactive oxygen species. Flavins do feature a radical intermediate which has the potential to react with nearby molecules. Reactive oxygen species are also generated from other cellular enzymes such as monoamine oxidase on the outer mitochondrial membrane, cyclooxygenase in the cytosol, and cytochrome P450 on smooth endoplasmic reticulum. Endothelial nitric oxide synthase can generate superoxide directly under certain conditions. NADPH oxidase and myeloperoxidase generate reactive oxygen species or reactive chloride species as previously described. Xanthine oxidase is an interesting enzyme because it usually functions as xanthine dehydrogenase, which uses NADP+, but under certain conditions it converts to xanthine oxidase using molecular oxygen and generating peroxide or even superoxide as a product. Xanthine oxidase is one of the enzymes implicated in the release of reactive oxygen species during hypoxia and more specifically reperfusion after hypoxia or ischemia. Other proposed mechanisms involve inflammatory cells, leakage from mitochondria, and enzymes such as cyclooxygenase and lipooxygenase. There's also exogenous sources of reactive oxygen species, which include ionizing radiation, heavy metals, tobacco smoke, air pollution, halogens, and certain solvents. Drugs and other poisons that generate reactive oxygen species include the chemotherapy drug bleomycin, calcineurin inhibitors, gentamicin, and the herbicide paraquat. Paraquat is a fascinating but horrifically toxic molecule that's very efficient at generating superoxide in vivo. You may have heard that both paraquat and bleomycin toxicity are both exacerbated by the administration of oxygen, which should make sense with that mechanism. So what do reactive oxygen species do in the body? Why are they an issue? Essentially, they can damage all major biological molecules, including proteins, lipids, and nucleic acids. That said, there is evidence that not all reactive oxygen species are bad. There is a low basal level of reactive oxygen species known as eustress, which is part of normal healthy homeostasis and provides signaling that regulates cell differentiation and response to stimuli such as hypoxia and exercise. Above those levels, cells experience mild oxidative stress or distress, and at the mild end, this may cause cellular damage, which could be reversible. Though at the severe end, you'll see irreversible changes and potentially cell death by various mechanisms. To start, we'll look at some of the effects reactive oxygen species have on proteins, specifically cysteine, which is the most sensitive amino acid residue. In this thiolate form, sulfur has an oxidation state of -2. It can be reversibly oxidized to sulfenic acid with an oxidation state of 0, or via this to a disulfide bridge, -1. This is the same mechanism that glutathione disulfide is formed, which is not a coincidence. These oxidation changes are detected by the cell and form the basis of redox signaling. As it's oxidized further, such as to sulfenic acid, which is +2, it becomes harder to reverse, and the most oxidized form is sulfonic acid, which is definitely irreversible and might require protein degradation. Reactive oxygen species or reactive nitrogen species can also affect multiple parts of nucleic acids. Typically, they react with the nitrogenous bases or the ribose or deoxyribose backbone. Bases can be modified, for example, with the addition of a hydroxyl group, which could potentially be repaired by the cell, and likewise sugars can be damaged, causing single strand breaks, which might require repair. Again, mild damage might be reversible, but with severe damage or failed repair, you may have double strand breaks or a mutation in the bases. The most dangerous form of reactive oxygen species damage is known as lipid peroxidation, which we'll need to discuss in more depth. It involves polyunsaturated fatty acids. For example, these are two more essential nutrients, alpha-linolenic acid and linoleic acid. There are lots of ways to describe fatty acids from a chemical perspective, though it's not often practical to use the systematic chemical name, and there are various conventions. The simplest is how many carbons, in which case both of these have 18. They are essential because the body cannot synthesize fatty acids with double bonds beyond the 9th carbon. To be more specific, linolenic has 3 double bonds while linoleic has 2, though this doesn't clarify where the double bonds are. There's an old convention that gave Greek letters to the carbons starting at the carboxylic acid end, with omega used for the final carbon. Using this, we could describe the bond position from the omega end, specifying omega -3, -6, or -9, and because this is a typical pattern, you could just specify the distal one, which is omega -3. As a result, you could describe alpha-linolenic acid as 18:3, omega -3, or 18:3 n-3, where n equals 18. By the same convention, linoleic acid could be described as 18:2 omega -6 or simply omega 6. We're going to use a simplified form of polyunsaturated fatty acid tail to discuss lipid peroxidation. It's a radical reaction, so you have to have an initiation step, in this case with a hydroxyl radical. The hydroxyl radical is highly reactive, so it abstracts a hydrogen from the lipid to form water and a lipid radical. The radical redistributes to the site of a double bond and reacts with molecular oxygen to form a peroxyl radical. The lipid peroxyl radical can abstract another hydrogen to form a peroxide and a new radical. As a result, this can propagate, slowly transforming polyunsaturated fatty acids into peroxides with different chemical properties and interactions. We've all had a crash course in epidemiology in the last few years, so this would be analogous to a disease with a reproductive number of 1, i.e. one radical forms one new radical. We also know that these can propagate until they reach another radical, which is usually in small numbers, so relatively unlikely. So that's pretty bad, but it gets worse. Do you remember the Fenton reaction? That peroxide is still sitting there and it can react again. If it meets iron 2+, it can turn back into a lipid alkoxyl radical and start a new chain reaction. This would amplify the propagation as long as there's iron 2+ around, as that is also consumed. Unfortunately, iron 3+ can also react with lipid peroxide and form a different radical. Worse than forming another radical, it also recycles the iron, making it into a reusable catalyst. This is exponential growth and it's a catastrophe for the cell. As long as there's oxygen available, the reaction is amplified until the cell dies by a unique mechanism known as ferroptosis, so called due to the role of iron. At this point, some radicals will start terminating by meeting other radicals as parts of the chain burn out. The other way the reactions terminate is with free radical scavengers, and this is what stops all cells from being destroyed by lipid peroxidation. Let's look at a free radical scavenger, another essential nutrient, vitamin E, in this case alpha tocopherol. As you can see, it has a somewhat polar head and a lipophilic tail similar to a fatty acid or a phospholipid and sits within lipid membranes throughout the body. Vitamin E has one major role, which is to terminate lipid radical chain reactions. It does this by becoming a radical itself 1,000 times more efficiently than polyunsaturated fatty acids and interrupting propagation of the chain reaction. The vitamin E radical is relatively stable because it's dispersed through an aromatic resonance structure. Of course, it still needs to be converted back to its non-radical form to continue to function. One way to do this is to react with another free radical scavenger, specifically the radical form of coenzyme Q, which you should recall also has a similar structure to vitamin E. Another method uses vitamin C as scorbate, which is an essential nutrient and free radical scavenger, except this one is water soluble, and so the exchange takes place at the boundary of the aqueous and lipid environments. The vitamin E radical abstracts a hydrogen from a scorbate, and a scorbate also disperses its radical through a resonance structure. Ascorbate radicals undergo a very interesting reaction called disproportionation, where two radicals convert into an oxidized and reduced form. The body has multiple other mechanisms to reduce the ascorbyl radical, such as MDHA reductase, which uses NADH and iron in the form of a Haem group as cofactors. Another is the broadly reactive thioredoxin reductase, which uses NADPH, FAD, and selenium. The enzyme can also reduce the fully oxidized form of vitamin C. Dehydroascorbic acid can also be reduced non-enzymatically by glutathione and indirectly by glutathione reductase, which also again uses NADPH. Now, you might wonder, if vitamin E only stops the radical portion of lipid peroxidation, the peroxides are still there and they can generate more chain reactions unless the cell has a method to deal with those too. Unfortunately, they do. Lipid peroxides can be eliminated by glutathione peroxidase in the same way it eliminates hydrogen peroxide. And notice again how many of these mechanisms require selenium, FAD, and NADPH. We're going to take a quick look at vitamin E deficiency. Vitamin E is a fat-soluble vitamin obtained from fatty sources such as vegetable oils, nuts, and seeds. Adults require an average of 10 to 15 milligrams a day, which is relatively easy to achieve, and with the body's stores, it's virtually unheard of to develop significant vitamin E deficiency due to dietary intake alone. Instead, vitamin E deficiency is either seen in association with disorders of fat absorption or vitamin E processing and distribution. Fat malabsorption syndromes such as cholestasis, pancreatic insufficiency, and in particular cystic fibrosis can lead to vitamin E deficiency. A third of the body's vitamin E is stored in the liver, and it's then distributed in very low density lipoproteins throughout the body. A specific autosomal recessive disorder known as ataxia with vitamin E deficiency results from a mutation in the gene for alpha tocopherol transfer protein. Functional vitamin E deficiency can also occur with A-beta lipoproteinemia because the body lacks the VLDL required to transport it to tissues. So what happens in vitamin E deficiency? We know it has one main job, which is to prevent lipid peroxidation in response to oxidative stress. We've also seen that vitamin C and selenium are necessary cofactors for vitamin E to work. This can be seen in animal studies where a diet completely absent of vitamin E produced only subclinical disease, but when combined with the absence of either selenium or vitamin C, caused deterioration and death over days to weeks due to lipid peroxidation and tissue destruction in the liver, CNS, and skeletal muscle. Vitamin C and selenium deficiency also have a synergistic effect together. In humans, vitamin E deficiency is best characterized as affecting nerves, the retina, and erythrocytes. In the nervous system, it causes a syndrome of cerebellar ataxia, areflexia with loss of the posterior columns. You can see a patient with vitamin E deficiency and a distinctive ataxic stance. It's worth mentioning that the neurological symptoms take years or even decades to develop, as there's very little vitamin E turnover in the central nervous system. It also causes retinitis pigmentosa, which is a progressive cause of blindness that starts in the peripheries. This is relevant because if it's caused by vitamin E deficiency, it's potentially treatable. Finally, it causes acanthocytosis, which is a distinctive spike deformity of red blood cells and a consequent hemolytic anemia. As mentioned in non-human mammal studies, it can also cause hepatitis and myopathy, especially with absolute deficiency, and it's been suspected of contributing to the development of dementia, as well as immune dysfunction, cancer, and chronic degenerative conditions such as atherosclerosis and infertility. Now let's talk about riboflavin deficiency, which has the unexciting name of ariboflavinosis, which means riboflavin deficiency disease. As we saw in this slide earlier, flavoproteins are essential for mitochondrial energy metabolism, as they are present in every pathway. Flavins are also required for heme synthesis, so deficiency also affects the cytochromes in the remaining complexes. It also affects folate metabolism, the activation of B6, de novo synthesis of B3, iron metabolism, and response to oxidative stress. This is where we reach an apparent paradox. It's common to have mild riboflavin deficiency. The symptoms are mild and severe deficiency is rare, and such that some describe it as a non-fatal condition. Why don't we see severe disease? It's clearly more essential than thiamine, and thiamine deficiency is rapidly fatal. The answer is that most foods contain some B2, which is adequate for essential functions. The body is also extremely efficient at recycling flavin groups from proteins. The body prioritizes the essential enzymes and pathways such as energy metabolism and essential tissues such as the central nervous system. Some enzymes are more sensitive to deficiency of their respective B2 coenzyme than others. Another mechanism might be the preferential conversion of FMN to FAD to preserve essential proteins. So what do we see? Instead of seeing disease in nearly all systems, like in thiamine deficiency, we see disease in the most vulnerable tissues, particularly those with high cell turnover and oxidative stress. The most destructive findings are seen in the mouth, where it causes inflammation of the margin of the lips, corners of the mouth, and inflammation of the tongue. More severe deficiency can cause inflammation of the skin. In the eyes, it can cause photosensitivity, conjunctivitis, opacification of the cornea and lens. FAD is required for heme synthesis, so it can cause anemia, which is typically normocytic and normochromic. Severe deficiency causes peripheral neuropathy and can cause functional deficiencies of B3 and B6, as well as more significant cellular damage. We generally don't see absolute deficiency in humans, but animal studies demonstrate the more severe findings. Animals deprived of all riboflavin die after around 7 weeks. This is much faster in juveniles due to high demand with growth. You typically see a failure to thrive picture followed by death from sepsis or multi-organ failure. Deficiency of vitamin B3 is known as Pellagra and is of more clinical and historical significance than vitamin E or riboflavin deficiency. The name comes from an Italian phrase meaning rough skin. Let's look at B3 metabolism. The two most common dietary or supplement forms of vitamin B3 are niacin and nicotinamide. As you can see, they have very similar chemical structures, and nicotinamide can be converted to niacin. Nicotinamide riboside is another exogenous form that can be used. Niacin is metabolized using two intermediates, nicotinamide adenine dinucleotide. This is known as the Pris-Handler pathway. We know it functions as a redox cofactor, but it can also function as an ADP ribose donor, which activates signaling pathways such as PARP and sirtuins, which are involved in response to DNA damage and redox sensing, respectively. NAD plus is converted back to nicotinamide in the process and then can be recycled to NAD via what's known as the salvage pathway. Finally, cells can actually make nicotinamide compounds themselves from the essential amino acid tryptophan. This is known as the de novo pathway and is the most complex, using numerous redox cofactors as well as vitamin B6. Due to inefficiencies and alternative branches, it takes 60 milligrams of tryptophan to produce the equivalent NAD plus as 1 milligram of niacin, although it could be argued that niacin is not actually an essential nutrient, but you'd have to make up for that deficiency with tryptophan. NAD plus is reduced to NADH with the addition of one hydrogen ion and 2 electrons, the equivalent of a hydride ion. The reaction is central to energy metabolism, and the NADH is often shuttled to the mitochondria to be oxidized in the electron transport chain to make ADP. NAD plus can be phosphorylated to the related molecule NADP plus. While they undergo the same oxidation reduction reactions, they have different functions. NADP plus is reduced to NADPH in the pentose phosphate pathway and with enzymes such as malic enzyme used in fatty acid synthesis. It is then used by enzymes responding to oxidative stress and detoxification enzymes such as cytochrome P450 and anabolic pathways such as fatty acid synthesis. I mentioned in the bioenergetics video that the ratio of NAD plus to NADH is markedly weighed towards the oxidized form. This means that oxidation pathways such as glycolysis or the citric acid cycle can run most efficiently because NAD plus is one of the reactants that generates the forward reaction. This is why alcohol metabolism inhibits the TCA cycle by producing excess NADH. Interestingly, NADPH is the opposite, with the ratio being 100-fold in favor of the reduced form. This is likely associated with its essential role reducing molecules oxidized by reactive oxygen species, such as oxidized ascorbate or glutathione disulfide. Okay, we're going to move on to B3 deficiency, known as Pellagra. If we look at a simplified view of B3 metabolism, you can see that there's a certain amount of redundancy from the core pathway, salvage, and de novo pathways. This means that a niacin deficiency also requires a relative tryptophan deficiency. As you can probably predict, B3 deficiency causes impairment of energy metabolism, detoxifying anabolic functions, and the response to oxidative stress, as well as impairment of some DNA repair functions from PARPs. Pellagra, the resulting clinical syndrome, is often described by the alliterative mnemonic dermatitis, diarrhea, and dementia, and sometimes with the addition of death. I'll start with dermatitis. This can be severe and potentially disfiguring. It occurs primarily due to the oxidative stress resulting from UV exposure. As such, it occurs in regions of the body exposed to sunlight, such as the hands, feet, face, and neck. The facial lesions can resemble the butterfly rash seen in lupus, and the rash surrounding the neck is characteristic and known as the Casal collar, after the Spanish physician who described it. Diarrhea refers to inflammation from the oral mucosa throughout the GI tract that often causes diarrhea. The pathophysiology is similar to that causing the rash, although oxidative stresses are food and bacterial toxins rather than ultraviolet light. Impaired energy metabolism may also be a factor, and rapid cell turnover certainly is, as seen with riboflavin deficiency. The reduced flux through the de novo pathway also disrupts the production of neurotransmitters such as serotonin, GABA, and glutamate. Serotonin requires tryptophan as a precursor. This, combined with impaired brain energy metabolism and oxidative stress, cause neuropsychiatric manifestations ranging from poor concentration or malaise to severe depression and progressive cognitive impairment. If you recall, the pathophysiological factors are relatively similar to Wernicke-Korsakoff syndrome that results from thiamine deficiency. This was a significant portion of an upcoming video on essential nutrients, part of a planned series of videos on nutrition. Please subscribe to stay informed of updates and future videos, and thanks for watching.